This is the first lecture of Chapter 6, which is primarily about the three-dimensional structure of proteins. So for Lecture 1, we're going to discuss what the different levels of protein structure are and some of the main features of secondary protein structure. So when we look at proteins and discuss their structure, in general what we're talking about is how these proteins are folded in terms of three dimensions. So the rules interpreting how a protein is folded kind of comes down to a scientist named Linus Pauling, who determined some rules for secondary structure. And so if we're talking about protein in terms of structure, we can think of primary structure as that first structure that occurs where you have a long amino acid sequence. So that's what we discussed in Chapter 5. What is the physical arrangement of these amino acids in the chain? Then secondary structure is going to look at local areas of repeating main chain structure. And so these are structural forms that are involving extensive hydrogen bonding between the main chains of the amino acids that are in proximity close to each other. Then tertiary structure is talking about how those secondary structural elements are arranged in terms of aligning towards each other. So where they are formed, where each secondary structure element is incorporated within the main protein in comparison to the other secondary structure elements. And then finally, some proteins have an additional level of structure called quaternary structure. And so not all proteins will have quaternary structure, but this is referring to the arrangement of multiple polypeptide chains relative to one another. So some proteins will have quaternary structure, others just have tertiary structure. So this is a subunit of hemoglobin, which is a protein we'll talk a lot about in Chapter 7. And hemoglobin is a protein that has quaternary structure. So this is one subunit, one polypeptide chain of hemoglobin, and then you have three other units that come together to form one core, and that is the quaternary structure. So if we go back to Paulus Lining's rules, he determined a set of rules that characterize what composes secondary structure. So according to these rules, bond angles and lengths should be like those that are similar to respective free amino acids. So there's no real difference in the freedom of motion between amino acids that are free in solution and the forms that these can take when they're in their long polypeptide chains. Then no atom should approach closer than their van der Waals radii to each other. The imide groups also have to be able to remain planar because those bonds between each of the amino acids has a planar structure. And then finally, you're going to end up having non-covalent bonds or hydrogen bonding that stabilizes this three-dimensional form. So when we look at in terms of the ways that these guys can rotate to each other, the bonds that these amino acids can rotate on don't have complete freedom of motion because we have those imide bonds between each of the amino acids main chain, between those carbon and nitrogen atoms. So we have two different angles that we talk a lot about in terms of secondary structure, and these are the angles that can rotate about this static planar form. So we have phi and psi angles, and this is looking at those angles between the C alpha carbon and the carbon of the neighboring of an amino acid, and the C alpha carbon and the nitrogen. So not all rotation angles are going to be favored equally here because we're going to be considering the side chain size and also the fact that not all forms, if you have a steric clash or have two atoms that approach too close to each other, that isn't going to be a form that we readily find. So we have three main types of secondary structure elements that will form in proteins. The first is an alpha helix. One of the things that you can notice here is that this is a helical form. So these main chains of the amino acids will circle around and form a tube, kind of like a straw. And it's stabilized by hydrogen bonding between the main chains of these amino acids. So every 4 amino acids away will have a hydrogen bond between the nitrogen that's incorporated within the main chain and the carboxylic acid functional group of a amino acid. So they're about 4 amino acids away from each other. You can also have a different form called a beta sheet. So in a beta sheet, instead of forming interactions with the amino acids that are in relatively close proximity, we have a very elongated strand that's forming, and the hydrogen bonding can occur between more distal regions from the protein. So it lines up kind of like a sheet of paper. The plane itself between the main chains is relatively flat, and the side chains rotate coming out or behind this sheet. Another type of helix secondary structure that we can have is called a 310 helix. This helix is slightly more elongated and thinner than the typical alpha helix. Generally, this 310 helix occurs in short regions and kind of introduces a bend or a turn into the protein's structure. There's oftentimes smaller residues like glycine that appears in this 310 helix, or prolines that kind of introduce a tighter form. So this is a proline that's within the starting region of this 310 helix. So when we describe the secondary structures in proteins, the main 3 types of secondary structure are the alpha strand, or the alpha helix, the beta strands, and there's 2 different types of beta strands. There's an anti-parallel version and a parallel version, and we'll look at what those are in more detail on the next slide. We have 310 helices. This also does meet the Pauling criteria, but we don't find it particularly frequent in proteins. A lot of times it's short regions. And then a polypeptide 2 helix, which is also kind of a unique form. So the beta strand itself kind of has 2 different types of beta strands that can appear. You have parallel beta strands, which means these strands are running in the exact same direction. So if we lined up the strands and looked at the N terminus to the C terminus, both strands would be running in that type of way. Or we can have anti-parallel, which means one strand is moving from the N to the C carbon terminus, and the other one is going from the N to the C in the opposite direction. So we can encounter both types of these beta sheets. In order to figure out which form you're looking at, you kind of have to look at where these secondary structure regions are occurring. Typically, if you're looking at protein structures, we kind of take a simplified form when we're looking at it in terms of the global structure, and instead of showing every single amino acid, we'll typically show it using what's called ribbon form. And so in gray, you can see the ribbon form for this secondary structure element, and that's this arrow. So the arrowhead is pointing in the direction that the strand is moving in. So the N terminus would be at the end of this form. The arrowhead would be close to the C terminus. So that's called the ribbon form. A lot of times if you're looking at the global tertiary structure in what's called a cartoon form, it's not going to show the amino acid backbones. It's just going to show this ribbon form. And so that's what we saw in this slide previously. When we looked at it in secondary structure, this is the cartoon form that's shown looking like a helix. But if you look at the backbone that forms the helix, that's showing all of the amino acid side chains. We simplify it a bit when we're looking at this tertiary and quaternary structure, and we're just showing it in the cartoon form, showing the helices, or if there were beta strands, it would show the beta strands here as well. So another type of secondary structure that you can encounter is called the polypeptide 2 helix. This is probably one of the most rare types of secondary structure that you'll see in a protein. It's not found very frequently, except in one main class of protein, and that is the protein collagen. So collagen has lots of polypeptide 2 helices, and these helices are rather unique because they are formed by a large number of prolines and hydroxyprolines, which are prolines that have had a hydroxy group added onto them. This is a very unique type of secondary structure. It's not encountered often. In an alpha helix, which is encountered in many different types of proteins, this is kind of showing what that form looks like if we look down the center. If you look at the center of the alpha helix, you don't really have any atoms in this central space here. Instead, you have the side chains all tightly packed and circling around, and then the side chains stick out into the visible surface, and these side chains are free to interact with other regions of the protein, or potentially, if it's in a solvent-exposed region, these side chains are free to interact with molecules of water or salts. If we look at it from the side, we can see that we have these hydrogen bonding interactions approximately every 4 amino acids away. That is what stabilizes this helical form. So if we're showing an alpha helix in tertiary structure form, it's just shown as a helical ribbon. So if we look closer at a beta sheet, this does a really nice job of showing how those side chains are positioned. When you have a beta sheet, they rotate, so every other amino acid faces the opposite direction. There's a really good reason for this. If we had these amino acids switched so that these side chains were all facing one direction, you would run into a lot of problems in terms of steric clash. So rotating the directions that these amino acid side chains face eliminates the steric clash that would potentially occur if you had them all in close proximity on the same side. The side chains are stabilized by main chain interactions, just like in an alpha helix, except that they're crossrise between the main chains on each chain. Then these side chains are free to interact with solvent or potentially with other regions of the protein. All right, so that's it for this first lecture from Chapter 6. I'll pick up with Lecture 2 and discuss what some of these interactions look like in terms of a Ramachandran plot and in terms of tertiary structure in some specific types of proteins in the second lecture.